there might be a few questions about the assignment that you guys did over the break. How did it go, Lisa? I've been overhearing that there's sadness over here. Well, that's all right. Tell you what. Why don't we wait either to the end of the period or whatever, just because we got some momentum here. Let's go ahead and get started with the class, and then we can talk about it at the end or whatever. We're going to keep building on what we had. We've been working, oh my gosh, a week ago, we were working on the idea that we were using the normal distribution, the bell curve, as a way of coming up with estimates of the probability of certain things, especially rare things. What was the odds that this unusual thing happened? Remember, we had those binomial distributions, and they were fairly rare things. Like, you know, they were, what, there was 40% of the cars were speeding. What was the probability to catch at least 60 cars out of 100 speeding, and so on? They were rare events. But the normal distribution was really good at things like that, at least estimating, giving us a sense of the relative frequency of those kinds of events. Today, as we move into chapter 10, we start seeing how we're going to be using the ideas that we've built so far about statistics and probability to make predictions about how systems will change. Not just a single event, like the next roll of the dice, or the next, you know, think about like a biology class we might have had where they talk about like, you know, genetics, like, you know, when you were in biology, didn't you? How about like where they were talking about like they were raising peas? Remember the peas? And there were smooth peas and there were wrinkly peas. Did you have that when you were in biology? He's nagging his head, so it's okay. All right. Well, that's just not one. Now we're talking about whole systems of things. And we're also going to see that we're going to be able to simulate or model these kinds of activities. Hey, we've been doing that, you know, using random things on and off all semester. Remember the day we were out there on the tiles and we were rolling dice on the tiles? And remember the days that we've had the dice in here to figure out other things? We do it. We've done it on spreadsheets and so on. Today we're going to be doing other ways of talking about using random processes to simulate how these kind of systems are going to change. Now, we're going to be using, I have some parts of it up here on the PowerPoint, and something has gone horribly wrong, as only happens when someone's coming to observe. I don't know why, but the font didn't work. So, if anything kind of rolls off the edge of the screen, we'll cope. Okay, I don't know why. I obviously did not choose this crappy font. I don't know what's going on. So today we're moving forward into section 10.1, which is called Markov chains. And this word Markov chain makes it sound scarier than it is. When they say chain in this context, what they mean is a chain of events. Okay. Something happens with some probability, and then something else happens with some probability, and then something else happens. Okay? And we can then figure out what's the likelihood of various outcomes over a series of transitions like that. And what we're going to be doing is we're going to start building on the example that they used on page 453. And they only do that to throw the blame at the book. To be honest, I'm uncomfortable with the example they used. But they explain it so well that I really wanted to come up with some better way to explain or something, but I was like, man, I'll just keep referring back to this one. So we're going to work with the one that they had. And the one that they were talking about was different socioeconomic classes. And again, I apologize, I don't know what's going on here. This was much nicer on my screen. I don't know why these icons are with the numbers on top. But whatever, we still sort of see what it is. And what they did is they labeled that there were 3 different socioeconomic classes here. And they called class 1 the lowest class on their socioeconomic ranking. See how he's got his pockets pulled out? And they called class 3 their top socioeconomic class. He looks like Mr. Top of Hat from Thomas or the Monopoly Money Guy or something like that. And then there's a middle class as well. Okay, this would not be my favorite choice of a way to explain Markov chains, but they did such a good job explaining it. Or when you go back and look at the book and things like that, you'll be able to tie it to what we did. So even though it's a little awkward to talk about socioeconomic classes in this way, they did it so much better. We'll talk at the end of the period about other kinds of problems we could solve using Markov chains. makes me a little bit uncomfortable about talking about these is that, well, the real purpose of these kind of problems that involve these Markov chains is talk about changes, transitions. Anytime we talk about a Markov chain, or we're going to learn about transition matrices and transition diagrams, it's about how things change. Well, let's take each of those three groups and think about how they could change. Well, from one generation to the next. If you have somebody in group one thing that could happen is their children are also in group one. When they grow up, they're also in that socioeconomic class. And the book cites some particular study and says, let's just say that that happens with a probability of 0.65. If you are in that class, there's a probability of 0.65 that you're going to end up in that class too. Hold on, let me just double check something real quick here. Similarly, there's a probability that you could end up in, sorry, that always freaks me out right at the time the bus comes, that my phone rings. I'm like, oh no. Anyway, so sorry about that. All right, so there's a certain probability you'll end up in group 2 and stay there. Your children are also in group 2. So for transition from one generation to the next, you're still in group 2, and there's also some probability that your next generation will also be in group 3. Notice, by the way, none of these probabilities are small. The way the book is thinking about this, there's a high probability your next generation will stay in the same socioeconomic group you are. But it wouldn't have to be that way. Another thing that could happen is you could end up where your children are in a lower socioeconomic group than you are. And that can happen with some probability. So, for example, there's a probability that group 2's children will end up in group 1. And they said that happens 15% of the time. And there's a probability that group 3's children end up in group 1. And that happens some percentage of the time. And there's a probability that group 3's children become members of group 2. Those are all the downward transitions. So of course there's also upward transitions, which I'll illustrate on here this way. Where a member of group 1, your children might be in group 2, or your children might even be in group 3. Or if you're a member of group 2, your children might end up in group 3. I notice that these probabilities aren't very big. But again, it would not have had to be that way. We could have chosen a different process to simulate using a Markov chain, like orbitals of electrons on an ion as it interacts with a photon. That's a more classic thing to do with a Markov, but this is something that's so hard to think about. So we'll work with what they got. This squiggly diagram that I drew here is not something I made up. This is called a transition diagram. It shows all the different paths that can happen as we move from one generation, or one iteration of this system to the next. In this case, from one generation of these families to the next. All the different paths, different people in different groups could be moving through in society. Or this could have been all the different orbitals of the electrons there. This could have been all the different colors of the pixels on the camera. This could have been, there's lots of different kinds of problems this can solve. But this transition diagram can get complicated really fast. Right now, we only had 3 states that the system could be in, and we only had so many ways that we could get from one to the next. Notice. No, I want to know what Luke thinks. Luke, what do you think about this idea that they divided people up into 3 classes? Do you think that people fit in those classes very well?
Depends on the person.
What? Depends on the person. Yeah, I love this. But notice, there's only 3, the right vocabulary word is discrete states the system can be in, right? You're either class 1 or you're class 2 or you're class 3, right? Okay, now in a physical system where you're talking about you're either in this state or this state, the switches are either on or off in a transistor or whatever. Okay, but I don't know that I buy that this really applies to people very well, right? You could be not necessarily very strictly in one case or another. But part of what's important here is that they have to be in a particular state. Notice that when they can go from one generation to another, or one iteration to another, all the probabilities have to add up to 1. There can't be other ways to escape the system. Notice, for example, we did not include the possibility that they don't have children. Right? That just wasn't even in here. The probabilities have to add up to 1. The transistor can either switch to being on or off, but there's no way, or we just turn it off and it's not part of the system, right? No. There are only discrete ways to do it, and they have to add up to 1. And in this case, if we go through and pick at this, every one of these does add up to 1. We could talk about person 2, and their next generation can either still be in class 2, or can become class 1, or can move to class 3. But the possibilities have to add up to 1. And same with the person in group 3. Their next generation, all the possible outcomes and their probabilities have to add up to 1. Well, once we have some probabilities, and we know that there's some chance different outcomes can happen, you've been in this class enough. You know what we're going to do? We're going to give this a whirl. So here's a group. Lisa, you want to work with Malia? I'll give you guys here. Yeah. If you want to come over there, or you go over here. I don't really care. Here we are. What? No. No, don't. Now, let's think about this for a second. You each have 20 people. And each of those 20 people is going to have a next generation. There's their child. You guys all have 20 people who started out class 1, right? On yours? Yeah. You guys have class 2, and you have class 3. Okay. And we know from this diagram that there's some probability each of your people, of your 20 people, what each of their kid will do. It's a game. Who played any games over Thanksgiving? Anybody play any games? What'd you play?
Team Fortress 2.
Did anybody play cards? Did anybody play Twister? Did anybody play or go to bingo? What'd you do?
I played cards.
You played cards. What'd you do, Lisa?
We played Monopoly.
You played Monopoly.
Yeah.
I like your answer. Monopoly. Let's try that first. How does it work? Okay, you move in. I haven't played Monopoly in years. Tell me how do you move in Monopoly? I mean, it's kind of the same sort of thing, right? This is kind of Monopoly. We're playing a game, right? How do you move?
Around the board.
How do you decide how far you move?
The dice.
Dice, yeah. And when you land on chance or community chest, what happens?
It's
You pick a card, right? What's in those cards? No, things, she says. What's in the Monopoly cards? Good things and bad things, right? There's gold, pass go, collect $100, $200, or there's bank error in your favor. There's all those cards, and there's some probability you're going to get a good outcome, and there's some probability you're going to get a bad outcome. See, here's the deal. The people in group 1 have different possibilities. It's like they're pulling a community chest card or a chance card in Monopoly, right? And there's some chance they're going to stay where they are, and there's some chance that they're going to move to a different group. Guess what? That's what's going to happen to your people. I have 100 cards in here. 65 of them say person 1 sticks in group 1. 28 of them say person 1 sticks in group 2. Let's see the possibility. 7 of them say person 1 sticks to group 3. It's the worst wheel of fortune ever. You get to decide, for each of your 20 people there, you're going to pick. Here's their destiny. My 8-year-old made these. I don't know why he made them so small. Person 1's next generation moves to 2. Then put it back, because otherwise you screw with the odds. Okay? Okay, wait. More.
Is that for grandchild?
No, that's just for child.
Okay.
They'll give you a certain chance that we're moving to child. Who played something else over Thanksgiving? Every Twister with the cousins. Anybody play Life? Anybody play any kind of game with a stupid spinner?
Yeah.
You did, sure. What the heck?
Oh, it's a twister.
Was it what?
Twister.
Twister. How does it work?
You spin the thing and it's like divided up into 4 sections, and you have right hand, right foot, left foot, and then there's 4 colors.
Yeah, the wheel sets your fate in the game, right? It tells you what the next step is, the next iteration is, right? Based on, what decides, you said it's divided into 4 parts? One for left hand, one for right hand, one for left foot, one for right foot?
Yep.
Okay, so are they equally sized pieces?
Yeah.
Okay, but if the game wanted to be rigged, because it's kind of funnier when they do their feet, right? How could they make the game rigged?
Made each section.
You see what she's talking about? Make the pieces of the pie bigger or smaller? Like, for example, if they really wanted to be funny, needed to be a small piece of it that was head, and you had to put your head on yellow or something like that, right? Or if they wanted to make it easier, they could put like the feet pieces bigger and so on. It's like the world's worst game of Wheel of Fortune, right? You're getting a chance and so on. And generation 2 here, in group 2. You totally need that. Here's a spinner. Star Wars game of some kind, I don't know. This is what happens when you put an 8-year-old in charge of finding these things. Here's your spinner. And I made this little thing that goes over the top of it. It's a little pie chart. And 18% of the pie chart is 2 goes to 3. 15% of the pie chart is 2 goes to 1. And 67% of the pie chart is 2 goes to 2. Now you kind of have to hold it down a little bit with your hand. But look, it's fate. Whoops, pretty good spin. Look. Oh, 2 stays in 2. 2 becomes 1. Ooh. 2 goes to 2, right? You're going to have to kind of hold it down, otherwise it snags on this thing. Okay? Fate. Fate. Wait a minute. What's another way we could do this? I kind of like this idea. We've kind of made some rigged games here. We made a rigged game that keeps people, that determines where group 2 people end up. We got a rigged game that decides where people 1 could end up. It sets probabilities these things happen. Who played video games over the break? Oh, okay. Luke. How does a video? Okay, some video games aren't very random, right? Pretty much the same bad guys hide, the same turtles hiding behind the same shell every time, right? But some games are very random. How does the computer do that? Is it spinning a wheel inside of there to determine whether whether the turtle's on the left or the turtle's on the right? I haven't played video games in 30 years. What do I know?
No.
How does it decide?
I'm assuming there's different code for different situations,
And how does it decide which one to use?
depending on what the player does.
Yeah, most video games are actually not that random.
There's typically a pattern.
Yeah, most video games actually there's a pattern, but that'd be kind of lousy in this, wouldn't it? But some video games are quite random. How about Tetris? Anybody play Tetris?
Yeah.
You guys know what Tetris is, right? With the tile, the little Russian music displaying while the tiles are falling down. They're very random, right? Someplace in there, there's a random number that is being generated that determines where the next piece is and what color it is and all that stuff and which way it's turning and so on. Computers are great at that. And you know me. one of our goals of the class is that we use spreadsheets to solve lots of problems. And it turns out there's a spreadsheet function called equals rand that'll just give you a random number from 0 to 1. Make your book out. So if you had on your book this table here that explains these probabilities that are on here, could you see how, like, if we were on group 3, you're on group 3, right? Like, if we were in the range of, like, at least 12%, we should do this thing. And if we were on this range of 36 wide, we should do, let me go here instead. You're group 3, right? So if you were in a range that was 12% wide, like maybe from 0 to 12%, like 0 to 0.12, if your random number was from there to there, you'd go this way. If your random number was between whatever 12 and 12 plus 0.36 is 0.48, you would go this way. And if your random number was greater than 0.48, you'd go and stay in group 3. Make sense? We would just use the random number to determine which of the 3 fates you have. I am so prepared. Except I thought I'd go more old school on you. Instead of them using a spreadsheet, because, you know, every now and then I talk about it, here's a page of random numbers. Before the days of spreadsheets and stuff like that, if they did random numbers for a study like this, they would consult the Handbook of Tables of Probability and Statistics of the Chemical Rubber Company. It was a thing. But here's some numbers for you. Well-tested, very random numbers. And I'm going to pick one at random. Here. That's your first number. We'll call that 0.67. And this one is 0.90. And this is what decimal point in front of each of these? Okay? So that's your number. So your group 3, that first one, you get a 0.67. 0.67 means you go from group 3 and you stay in group 3. You see what's happening? She got her first random number on there was 0.63. That's in this range. So she's currently going from group 3 and she's going to stay in group 3. Okay? And then if they get a 0.37 for their next number, well, that's in this range. So they're going to stay. I'm sorry, no, they're going to go from 3 to 2 in the second generation. Right? You're only filling out now the table for children. All right, you all have 3 different ways of simulating the random numbers that let you model what the children are going to be like. Well, not what the children are going to be like. See, that's why I hate this game. Which of these classes they're going to be in. All right, so work together and simulate the generation for 20 families. Usually once you have one, you just work your way down. Just out of curiosity, count up how many 1s, how many 2s, how many 3s you have over there. I know, that's not the best choice of a way. I was happy he found a spinner. It wasn't such a great...
1 to 3. My birthday is this weekend. My 18th is Thursday.
Wow. I don't know why there's a baby.
Stop anytime. Hey, I have a question.
Yeah.
So, have you ever watched the show Deutschland?
No.
Is that what it's supposed to be?
Okay, well, it's on
supposed to be 67,
Hulu, and
so
I
that's
highly
pretty close.
recommend
Oh,
it.
darn
It's
it.
good.
Okay.
It's about the Cold War.
Neat. I've heard of it actually.
I guess.
I watched, my sophomore year, I watched the first couple of episodes in class, which
No,
was
that means-
shocking.
Some of them are
he
gonna
let
be
us
dumb,
watch
some of
shit
them are
like
gonna
that.
be
Yeah.
geniuses.
But,
Yes.
so that's what we watched,
They're
and
special.
then a friend gave me
That's the word.
her Hulu password.
Uh-huh.
So that way I could watch the rest of it while then her mom turned around and changed it.
Got them all?
Yeah.
Just out of curiosity, just like baby, can you total up, how many class 1, how many class 2s and how many class 3s you got? Are you guys are done, so you don't need this table anymore. All right. How many of you guys got left?
Just
A couple more. Okay. It's like you're in charge. You're the autocrats.
this is the last one.
Dare I say, economic gods controlling the fates of these families. Right? Mm-hmm. All right. You can, while you're doing this, you can just kind of curiosity, sum up how many of them you got for each of them. What happened? Do they mostly stay in the same economic class? Yeah, mostly they should have. Because that's where the highest probability was, right? Whereas there's some transitions that were much harder to make, right? Going from class 1 to class 3 was only a 7% chance. And did you guys get any 1 to 3s?
Yeah.
Maybe 1? 1 or 2?
You got
2? Okay. So you got a few of them, but these were just these simulations here showed that it was not that easy to get to. This is a mess. This transition diagram could get complicated really fast. We only showed 3 different nodes here, 3 different discrete states it could be in. But realistically, this could have quickly become many possible states, right? Markov chains and transition diagrams like this are used, for example, in video and compression and encoding, where each pixel has different states it can be in, and what is the probability it'll change to different colors and so on. Well, there could be a very large number of states here. This gets messy way too fast. We need a better way to do it. We're going to call it a transition matrix. A transition matrix is actually pretty close to what I had up there written on the board. It's actually what we kind of had to use over here on Lisa's book to help us a little bit. But it's the same information. On the rows here, that's the state you're currently in. And then the columns are what state you might move to, you might transition to. And you can see this is the same information, right? Like being in group 1 and staying in group 1 is 65%. Being in group 1 but moving to group 2 is 28%, and so on. This is called a transition matrix. It's just a more orderly way of representing the same information, because you could see this could get big fast, and it's just a matrix, right? If I had even one more state on this diagram, it'd start to get pretty hard to put it in PowerPoint, wouldn't it? There'd be just too many arrows and too many colors and too many whatever. The transition matrix, I can make this as complicated as I want. Again, I forgot that I had a slide here, and notice it flows off the edge of the slide anyway because of the font problem. The rows are the state you currently are in, and the columns are the state that you are transitioning to. And the probabilities are what are the entries of the table. We only usually refer to, I had them numbered 1, 2, 3, and 1, 2, 3, but it's really only the kernel there of the matrix that we actually talk about as being the transition matrix itself. Your book is going to point out that there's a number, not just any old matrix you'd make would count as a transition matrix. For one thing, it has to be square. But any matrices aren't square. Clearly, this has to be square because there's a certain number of states, in this case 3, group 1, group 2, group 3, that you can start in, and they have to be able to end in the same set of states. Okay, so there can only be the same number of rows and the same number of columns. It has to be a square matrix. Your book also points out, for example, that all of the entries are obviously going to have to be between 0 and 1 because they're probabilities. No negative numbers, no numbers greater than 1, they're probabilities. They can be zeros, they can be ones, although that's going to make for a very strange kind of matrix. If the probability of making certain transitions is 0, you might get stuck, right? Where you can't transition out of a particular state. And this is a more obscure point, but notice that the sum of all the rows has to be 1. Because these are the ways, like for example, these are the ways that we can transition out of state 1, out of group 1. Well, there's got to be, you have to go one of these 3 ways. This one plus this one plus this one, therefore has to be 100% or 1. We're going to use the symbol P for this transition matrix. And there's going to be all kinds of nifty matrixy things we can do with this, like multiplying them and adding them and all the tools that we learned back near fall break of things we can do to matrices. We're going to be doing to this guy. But he's going to give us a way to start simulating how these Markov chains are working. Again, this was in very different fonts when I made it help figure out what's going on. But the transition matrix, according to the book, has to have these 3 key features. And the series of events that you are generating using the transition matrix is the Markov chain. On your little worksheets that you have there, you're making 20 Markov chains. Okay? As we're transitioning each of these families from one state to another over a series of generations. Notice that they have to be discrete states. That means like they can't be halfway in between or something like that. You can't be in group 1.5. Okay? Again, when it comes to people, maybe this isn't the best explanation, but a physical system, you can imagine, where the color of a pixel or the state of an electron or something like that would be in different discrete states. And the outcome of the experiment has to only depend on the present state. When you guys drew over here, and you drew a little card from the cup, the only information that went into this is which group you were from, your parents were from, right? It didn't include information about what neighborhood you were in, what schools you went to, how much money your grandparents left you, do you tend to play the scratcher tickets at the lottery and win big money, right? Nothing's in here. The only information that depends is what you're doing now. The real world, of course, that's not right? Including things like what happened in previous generations could matter, right? Grandparents had a bunch of money, could make a big difference as to what the grandkids are doing. But that's not the way Markov chains work. We only consider the present state as a way of moving forward. Again, this makes more sense in like a physical world. If you're talking about like, a photon is hitting an atom, what will it do? It will excite the electrons to a higher valence orbital. It will ionize it, whatever. Well, what happened to it in the past doesn't have anything to do with it. But in a system like that, that's a little harder to think about, so instead we're thinking about people. Another important one that's clearly not right. Well, I think I had notes about each of these things on there. Yeah, I did. Okay. Another important, final important one, is that these probabilities can't change. By definition, in these Markov chain type processes, from one generation to the next, we're going to keep the probabilities the same. We are going to not change the probabilities of us moving from one class to another, from one generation to another. Again, from a physics point of view, that makes a lot more sense. In a people point of view, this is not really a very realistic assumption because things would change, right? Different tax policies might move people, tend to move, change the probabilities of people moving from one group to another, for example. Okay? But we're going to just leave the transition probabilities the same from one transition to the next. Hey, let's keep building your table. How about grandchildren? Now you've got the children, and you've got their possibilities as to what what group they'll be in. Now you need to be able to simulate what happens to each of them. What social group Grandma and Grandpa were in, your first generation, no longer matters. The only thing that matters is the parents, the ones that you just wrote down. What are their kids? So, for MJ and Haley, you need 2 more cups, don't you? Because these are people from, if you have a parent, if one of these what you wrote down here, if you have a child, let's say, who is in social group 1, you want to use this to find out where their children go, right? I'll let you fill those up. Here's 100 tickets of group 2, of which 15 tell them they move from group 2 to group 1, of which 67 or something like that tell them they stay in group 2, and 18 tell them they move to group 3. And here are 100 tickets for group 3, of which 12 tell them they move to group 1. 62 say that they stay in group 3, and whatever the rest are, they go to group 2. Make sense? You're going to have 3 different pots here. So here you'll use group 1 to figure out what happens to their child. Then you'll have to use group 2 to do this one, right? All right? Wheel of Fortune, folks. You're going to do the same thing. They already had a wheel for group 2. All right? Now they have a wheel that represents the odds for group 1 and group 3. These things are a pain in the butt to put on and off. Here's what I would recommend doing. Let's just put group 1 on here. I'll let you do it. And just do all the ones that are 1s right now. Then take it off. Do all the ones that are group 2s. Don't take it on and off 20 times. Does that make sense? You'll be really sorry if you do it too much. Group 3, you have it easiest as long as you keep things straight. Right? All you got to do is, start somewhere on your table here. Okay, this is a 3. So you use the bottom row of the table there. Right? This is a 1. Use the top row of the table. This is a 2. Use the middle row of the table. Okay? So as long as you keep it all straight, you have the easiest one. Okay? Alright, so everybody simulate what happens to the grandchildren. And when you get done, just out of curiosity, add up the 3 different groups just to see how many are in each of them. You can add them up over here too. How many people now do you
Oh,
have?
I-
Oh, I see. So now there's 10 of them who are in? Okay, so now after 2 generations, only 10 of them are still in group 1, right? The rest of them have segued into one of the 2 other groups, right? It's becoming less and less important what group grandma and grandpa were in, right?
Hey, can I use the restroom?
Yeah. We'll be moving on here pretty soon. That's up to you. Okay, I'm gonna let you make a choice of that one. How about your group? You had 3s. How many of them were still in 3s? Notice how I started with 20 people in group 3 and now only 4 of them are in there, right? So that's about how many she's got. And they started out with group 1. How are you guys doing over here? This is from like the world's worst game. I dread it whenever he gets this spitter out. It's like this stupid game I don't understand. Anyway, all right. How important was it now how rich grandma and grandpa were?
Not important at all.
That's not to be important at all, right? What if those probabilities of staying in the same class had been higher? Each of them had about a 50 to 60% chance of staying in the same socioeconomic class. What would have been the probability? What if it had been 99? What if it was like the Middle Ages? If you're born a serf, you die a serf. Your kids are a serf. You're a peasant. They're a peasant. You know what I'm saying? And if you're a king, your kids are kings. Your kids are princes until they become kings, and then princesses, and so on. Right? Right? How important would it be then who your grandparents were then? So it's getting really important, right? See how these probabilities in this transition matrix start mattering a lot? Now, we could have done this the painful way. Remember Bayes' theorem? Where we started doing things like this? We could have started off with somebody back there in the back row who was in group 3. We could have assigned probabilities of the transition to group 1, to group 2, group 3. And then for each of those, we could have branched 3 more times and assigned probabilities. We could have done the whole conditional probability thing. What was the probability of being in group 1 given that grandpa was in group 3 and all that kind of stuff? And it would have been a huge amount of work. And we survived it back on the last test and so on. But we really don't need to do it that way. Although we certainly could, but now we can instead use this matrix to start figuring out these probabilities. So far you've been doing this by modeling. And I love modeling. Modeling is an important goal of the course. We can use these random numbers to solve all kinds of problems, but they do at some point become kind of hard to scale. What if I had said, instead of doing 20 people, you had done 1,000? How long would that have taken? A really long time. Especially these guys with a spinner over here, right? That would have gotten to be kind of cumbersome, right? Oh, we could have done it with a spreadsheet and used the equals rand function. And we could have actually done it. But you know what? We've got this matrix here. And this matrix is going to start telling us what we could do about it, start figuring out these probabilities. We don't actually need to do all this. Look, we could use the tool from the last, 2 chapters ago. We could use Bayes' theorem and figure out these probabilities. Given grandpa is in class 3, what are the odds the grandchildren are in each of these 3 classes? We could do that. We've done it before, but it's a lot of work, and it certainly gets very complicated the longer this tree gets, right? If we start putting out more generations, there has to be an easier way. And of course there is, but that's why I'm leading you over here. I mean, let's say we wanted to go out to the 5th generation on here. I hope now that you have filled out 2 columns of this table, you're beginning to feel dread. The idea of going all the way out to the 5th generation here starts sounding fairly horrible, right? I mean, maybe you're having fun picking the different tickets. But maybe this starts seeming like you need a better way of doing this, especially if I had more than 20 people on there, right? Let's think about what we could do using our matrix knowledge, our matrix brains that we spent so much time building before we fall break. I mean, we got a matrix, P, and this matrix tells us about the probabilities of all these transitions. And what I really did here was I took this transition here and I applied it twice. I mean, a way to think about that would be like effectively we're squaring that matrix, right? P times P. We applied it twice to the same group. And I don't mean that kind of metaphorically. Sometimes we use in math, we use those idea of like, we did it twice. We need to kind of metaphor. No, I mean literally. Let's go ahead and do our matrix math. This time, remember matrix multiplication? This times this, plus this times this, plus this times this. And then this one times this one, and this one times this one. Oh, it's clumsy, but you guys were great at it. By the time we got done with that matrix chapter, I could quite a problem that you guys would get wrong. So if we're going to have that matrix that is our probability, that's our transition matrix for one generation. Our transition matrix for 2 is just going to be p times p, which works out to this. All I did there was I just did the matrix multiplication. I just multiplied matrix p times matrix p, and I get this new matrix, p squared. Andrew, do you think p squared is a transition matrix? What did it have to be a transition matrix?
Had to come from.
It had to be square. Remember that rule? Is it square? Yeah. The numbers inside of it had to all be probabilities. They look like probabilities. There's no negative ones. There's no bigger than ones, right? And the tricky one was each row had to add to 1. Huh. Alright, so far so good? Just out of curiosity, I went and tried it while you guys were doing that. I was over here, and I actually put it in. I had thought about doing this until you guys were doing it. And let me zoom this in a little bit. Where's the view? There it is. Zoom. Let's make this a little bigger. Here's P. Here's our P matrix. So I just used, if you look over here, you can see I used the matrix multiplication function. And I got that same matrix that's on the PowerPoint slide. And just for fun, I went over here and I added each row. And sure enough, they do add up to 1. Just thought I'd, show. So this is a new transition matrix. And we could do it. We could have skipped the first generation there. We could have just used these probabilities. And they would have given us the same distribution of how many we started with. When Grandma and Grandpa were class 1, what are the odds, what are the probabilities the grandchildren will be in class 1? About 47%. How many of the, after you did 20 of them, how many of the grandchildren were in class 1? It was about half, right? Yeah. Group 2. Did you get a little over 50% of your people were still in group 2?
45.
You got 45%. Okay, well, it's the damn spinner. Right? And group 3, you had not very many at all ended up still in group 3, did you? Yeah, definitely not this, but probability. We only did 20. If we had done 20,000, they get closer and closer, right? All right. I won't. There's an example they did. This is an example in the textbook where they actually showed they were just reading the table. We just did an example of reading the table with you guys as another one. Find the probability that the grandchild of a class 3 individual will be either class 1 or class 2. Well, here's the probability of class 1. So here's the class 3. There's the result. That's the probability he'll be in class 1. There's the probability he'll be in class 2. And I apologize, the boxes didn't line up right because the font messed up. And then, well, the probability he's in group 1 or group 2 is the probability he's in group 1 plus the probability he's in group 2 minus the probability he's in both groups, which has to be 0. And you can do it, and it's no big deal. That was one of the examples in your books would have just been. And you can see we could do this over and over again.
Can you go back to the other screen?
Sure. Everybody's afraid to jump in. Yeah, this one?
Yes.
So yeah, this is the probability that they'll be in group 1. This is the probability the grandchildren will be in group 2. So the probability they'll be in group 1 or group 2, that's just our, what is that called, union rule probability? Probability 1 plus the probability 2 minus the probability they're in both groups, which that can't happen because they're exclusive. Right? Can't be in group 1 and group 2 at the same time because what's the right word? Discrete. Alright, so we could just add this up. Whatever. Another way we could have done it is we could have said, what's the probability they're not in group 3, and just done 1 minus that. That would have been fine too. Alright. I mainly put those other columns, though, on that table to give you dread. Because dread is an important emotion to have in a class the first day after Thanksgiving. I don't really want you to fill out all those tables. I mean, you've already begun to figure out, oh, for a few, this isn't the end of the world. But what if we're talking about a whole population? We're saying, for America, we don't have to do this like, if we wanted to simulate where the socioeconomic classes will break down in 2 generations, we can do that afterwards. What will the distribution of the economic classes be after 2 generations or after 5 generations? We really don't want to do one Markov chain at a time. Okay, that's going to be a whole lot of math and a whole lot of some kind of random number generation, be it drawing, be it spitting, be it random number generation off of tables or off of the rand function on there or whatever. But it turns out we don't need to. Say, for example, let's say we have these groups. Let's say we've done some kind of study and 21% of Americans are in group 1, and 68% of Americans are in group 2, and 11% of Americans are in group 3. And, you know, obviously it would depend on how you define the groups and all that stuff. But we have some kind of summary here. We know about that for the whole group. Well, we could ask, well, what is the distribution going to be for the next generation? Or 5 generations in the future, or whatever. Well, I really don't want to make 342 million Markov chains, right? But I now know what the distribution is. I could call that, if your simple uses the symbol X. So here are the distributions. 0.21 are in group 1, 0.68 are in group 2, and 0.11 are in group 3. I don't know why I used the symbol X naught, but it did in your book. For a little row matrix that just says that information. How many are in each of the 3 classes now? And if we just do a little, your spidey sense is tingling. You know where this is going. I've already warned you that we're using our matrix skills, right? So, if we have a little row matrix here that tells us this, and we've got a transition matrix that's the right number of rows and columns to multiply them, you know what we're going to do. We're going to multiply them. Could we add those 2 matrices? Remember from back when we did matrices? Could we add x naught plus p? No, they're not the right number of rows and columns to do that, right? Could we compute the inverse of x naught? No, it's not square. We can't do all of our other tools we can't do anyway. But we do have the right number of rows and columns to multiply these 2 things. So let's multiply them. And we multiply what we got now, the distribution what we got now, times our transition matrix, and we'll get a new set of numbers. And this is after 1 generation. Now, instead of having 21%, we have 25% in the lowest class. Instead of having 68% in the middle class, we now have 55%. And instead of having 11% in the top class, we now have, whatever, almost 20%. I could relay that information up into here. See, I didn't have to run 320 Markov chains here. 320 million Markov chains. I just knew what the distribution going into it was, multiplied that by the transition matrix. That was just using that transition matrix P. What if I had used P squared? What would I be finding out if I had multiplied x naught, the distribution of people now, by P squared? What would I be finding out? What the distribution of the grandchildren will be. What if I had multiplied it by P to the 5th power? P to the 5th power times x. I'd be finding out what the distribution will be in 5 generations, right? I don't know what any individual is. I'm not going to know what that first row of the Markov chain is, but I know across 320 million people or whatever, I know what the distribution will be. And in fact, we could do that. Let's go do that. So let's start off with an x naught. Let's just say 20% of the people are in group 1, 70% of the people are in group 2, and 10% of the people are in group 3. Okay? I could take, so x naught times p would be, that is the first generation. And I could take the matrix multiplication, we've done this a zillion times, x naught times p, and we would get how the next generation will work out. We'll go from 20% in the lowest class to 24%. We'll go from 70% in the middle class to 56%. And we'll go from 10% in the top class to 19%. Or we could do the same, I'm going to clear out these ones over here. We could do the same thing for x naught times p squared. We could say x naught times p squared. And, whoop, didn't like that at all. Oh, I know why, because I forgot the m mult. X naught times p squared. And we find out that now 26% of the people are in the first class, 51% are in this middle class, and 21% are in the upper class. And we could just keep going. We could have had p cubed, we could have had p to the 4th power, and we could have had p to the 5th power. They're a little clumsy to do up here in front of an audience, you know what I'm saying, to just keep multiplying, but we could get it all done. And we can find out what the distribution will be in 2 generations, 3 generations, 4 generations, and so on, without doing all those Markov chains. Neat! We don't know what any one person is doing, but we know the distribution across the whole population. Okay. Like I said, it's a little hard to apply this to people. The rules change, the tax policies change, the attitudes change. This doesn't work as well for people. A classic problem in a textbook is like, in this election, this percentage of people voted Democrat, this percentage voted Republican. We know that from one election to another, this percentage of people who voted Democrat will vote Democrat again, and this percent will flip. This percentage of people who voted Republican, and then this percent will flip. And then you can model how like the electorate will change. But realistically, it's not that simple, right? I mean, it's about the people who are on the ticket. It's all, I mean, those things only work so well. This is really much more used for things like video encoding, where you're figuring out the probability that like a pixel will change color from one frame to another. Or like I was thinking, anything quantum, the changes in the electron states and so on. These are very classic things. You shine a beam of photons through a gas, and right now you have this many gas atoms that are ionized, and this many that are reflecting, and this many that are scattering, and it changes. And as each interaction with the photons happens, how will the gas change? Classic example. Mostly this is used like in physics and computer science type applications. Because we're just starting with this. I think in your homework you do one about sales at a dry cleaner, where they're saying like, you know, this percentage of people will stick with Johnson's dry cleaner, and this percentage of them will switch to Luke's dry cleaner, and so on. Okay, well again, it's not that simple. But to use it as it's that simple. So what are we going to do with this? A relatively small set of problems. On page 459, and I'll get this up on It's Learning, I just don't have it yet. You have a set of problems here that are mostly about, this 1 through 14, is mostly about making sure you know what are the properties of these transition matrices, the transition diagrams, and so on. Like they give you a matrix and they say, is this a proper transition matrix? The relatively quick problems. It looks like a lot, because we hardly ever have a list like that. But it looks like a lot, but it's not. Then you have a set of problems, just 3 over here and then 3 over here, that are different kinds of story problems involving Markov chains. Doing the kind of things we do. Alright. We only have 10 minutes left. You might be wondering, what about that email that Dr. Shruggy sent us about a pop quiz? Yes. Over the Thanksgiving break, I was looking across here, and I was like, oh yeah, we usually do a pop quiz as we cross from one chapter to another, right? And we call them pop quizzes because that's the category we have. Anyway, on the syllabus, that's quite a category we have. And I sent you an email that said, be prepared for a pop quiz. What I'm going to do is I'm going to send you home with the pop quiz about chapter 9. Okay? It's not something like, it's not a test, it's a pop quiz. I think it's like 6 or 7 questions about what we did in chapter 9, just making sure that you get the basic concepts. Here's the deal. Don't use it as an open book or anything like that, okay? I realize by sending you home with it, I can't stop you from doing it open book. But here's the deal. What do we really do with the pop quizzes? The pop quizzes are really for me to figure out what we need to review in the chapter we just finished, right? So I mean, frankly, if there's something you don't understand, you're better off getting it wrong so that we then review it, than to be like, well, if I dig around in the book, I'll find it. Right? Okay? Yes, you'll get a couple more points on the pop quiz, which is worth the equivalent of one homework set. I can live with that. You know what I'm saying? But you'd rather get it right on the test, right? That's worth much more. All right. Obviously, another possibility is just come talk to me about it. I'd love to talk to you guys about this. All right? So, I'm going to give you, this is this homework set, and you're going to complete the pop quiz. All right.
We don't have an exit ticket.
Yes, you do.
Why?
It's only like 4 little questions. Why don't you guys go ahead and complete the exit ticket now before we leave the classroom? Yes. Now, this took a little longer than I was expecting. I was hoping to have about 20 minutes at the end to talk about homework. Tell me which one you're having trouble with. I know that you said there was some that made you cry.
Well, I was just joking. But 23, I didn't get.
Mrs. McNamara made her cry.
23, I didn't get any of it done. 24, I got all the way to part B, and 25, I got all the way to part B.
23, 24, and 25. This is coconuts, drug effectiveness, and flu inoculations?
Yes.
All right. Let me think about this for a minute. Go do the exit ticket while I think about what to tell you about these problems. Oh, I love this one about the coconuts.
Do you want our homework?
Well, that's what I'm trying to decide. How are you doing on the homework, Lisa?
I didn't do 24 or 25.
24 and 25? And you got stuck on 24 and 25?
I didn't get 23.
You didn't get 23, the coconut problem?
Yeah, because
We ran out of time today.
I have the rest of it then.
It's,
Do you want me to look?
yeah.
24 and 25, but I guess on 25 because it wasn't on the chart, so I'm just like, it's close to 0.
What?
Close to 0.
Wait a minute, what?
Yeah,
It like all the Z scores, like I was getting like negative like 4s and stuff,
Yeah.
and they're not on the back of the chart.
Yeah.
I have all 6 of you. I have an exit ticket for you. Okay. Which one are we talking about? 25. A flu vaccine has a probability of 80% of preventing the flu. County Health Office inoculates 134 people. Find the probability exactly 10 of the people get inoculated, they get the flu. No more than 10 people get the flu, and none of the people get the flu.
Like the back of the book even has the answers as like 0.0001.
Okay.
Yeah, and it,
So, there's a binomial probability here, right? There's a probability the flu vaccine works. All right? That probability is 0.8. Okay? We have 134 people who get the flu shot. Okay? So right off the bat, just before we even look across this thing, what's the expected number of people who will be okay? The expected number of people who will be okay will be 134 times 0.8, which is whatever it is.
107.2.
Yeah, how many?
107.2.
107.2 people will be fine. 134 times 1 minus 0.8 is how many people will get sick. What does that work out to?
21.44.
21.4? What?
Yeah, like 44. Oh, then I squared it. Sorry, I already squared it.
You did square to this? I was saying,
Aren't
that
you
doesn't add
supposed
up,
to
does
square
it?
it? Wait a minute, what? I'm so confused.
square root.
This is what I did. Yeah,
That is not
like, not, oh, I totally
Okay.
got rid of it.
I'm not worried about what the number is right now.
Okay.
Okay. So, there is some number of people who will get the flu. Somewhere around 107 people is what we are expected to be fine. Okay? But there's some high probability that all 134 are fine. There is some probability that 10 people? 124 people will be fine. There's some very low probability that none of them will be fine, right? So what you need to do is you need to figure out the z-scores for each of these possibilities, right? So we know the mean is whatever this was over here. We can find that standard deviation, which was what? N minus p or something like that? Or 1 minus p? Is that what it is? I can't remember that. It's been 10 days. I can't remember. Whatever it is, right? But you have the standard deviation. So, to find the z-score associated with, say, 124 people being okay, it will be 124 minus 107 over whatever that standard deviation is. But you'll get some z-score, right?
Yeah.
So that is the probability that you go look on page A13 and A14. That is the probability of this part of the curve. All right? So at least, no, that is the same thing, right? So that would be 124 or fewer are healthy, which is the same as 10 or more get sick, which I think is part B of the problem, right? 10 or more people got sick is this part of the curve, right? Exactly 10, we'd have to do that thing where you use from 123.5 to 124.5, and we'd be figuring out this little rectangle right here. That's two different z-scores, and we just find the difference between them. Okay, we're going to need to spend more time on this because this z-score stuff is important enough that we don't want to leave that behind. It's in the course assessments and all that kind of stuff. So here's the deal. Let's not submit your homework today and bring it on Wednesday. Between now and then, though, if you got stuck on those, I want you to come talk to me, okay? Or send me email or whatever, and don't wait till like Tuesday night, okay? Come see me today or write to me tonight or whatever with what specific problems you were having, especially now that we've kind of looked at them a little bit, okay? So that we can have a plan of attack. We're not just going, oh, 23, I still don't know how to do that coconut one, okay?
So do you still want us to go ahead and try to do the pop quiz?
Yes, so we do have a little bit of stuff here. So today, you're going to do the pop quiz. I mean, it's neither pop nor quiz when you're taking it home, but whatever. And then you have this relatively little assignment about today's Markov chain stuff. And then at least be able to articulate where things went wrong on 23, 24, and 25, and send that to me so that I can be prepared. Or come see me, or whatever. Okay? All right, kind of a mess. Things just ran a little longer than I was expecting. All right. Now,